My name is Roger Fritz. As many of you know, I have a group called the Nikola Tesla's Collaborations. It's been developed over about the last 15 years of people that have joined, shared concepts, ideas, growth, especially in the electrical industry. Um, I've followed Nikola Tesla for years and truly believe in a lot of his original principles because he was the developer of the AC alternating current system that everybody plays with today. Um, I always like to start out briefly. I've done a lot of work with the power companies and always to make sure that people are very much aware, that we're dealing with high voltage items, something you can't see and touch, but when you touch it, you don't normally get a second chance. So I always try to bring that up in the first part of our conversations. Um, a bit of background on myself. I've been in the motor and drive industry for my entire life. My father started back in 1953 in the motor industry, even originally started putting up wind chargers before there was power built in part of the rural Nebraska. Um, you also see my grandson. My grandson is fourth generation in the family. Um, we're very much motor control people, and once I came across what I've seen with Smart D, I said, this information has got to get out and explain to the world because I've installed thousands of VFDs, and I've always had to deal with a lot of the auxiliary issues of a, IGBT transistor from the GTR, days to the regular IGBT that's out today. But, now this new technology needs to be brought forward and, people make it aware of it. Today we're going to have with us the CEO of Smart D. Um, and I want to share that. Also, I put on the link that if you do want to join this group, I do own a copy of this, what I call the Tesla Bible, which shows all the original machines from, slip ring type motors, DC machines, AEC machines. I've been very fortunate to get that in my career. And we'll start out real quick with just a quick introduction here.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. A circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will at once establish the superior adaptability of alternating currents.
The Clean Power VFD produces a pure sine wave outright, eliminating the PWM drawbacks. It also brings additional benefits such as more energy savings, a reduced footprint, and simplified installation and maintenance. Common mode voltage is created by VFDs switching IGBTs on-off continuously. This causes wear and tear on the motor bearings. The first sign of bearing damage is audible noise due to the bearing balls traveling over the pitted and frosted areas. How are these pitted and frosted areas created? Fast switching of the IGBT creates parasitic capacitances in the motor. Common mode voltage and capacitances are sources of a shaft voltage. Shaft voltage causes arcing through the bearing lubricant, which results in pitting on the bearings and fluting on the bearing races. dV/dt of the common mode voltage in the stator windings generates pulse currents flowing to the rotor. Part of this current flows between the inner race and the outer race of the bearings, causing heat in the lubricant. Common mode voltage generates an electric charge stored in the parasitic capacitance between the rotor and the stator. When this charge gets high enough, it breaks the dielectric insulation and is discharged through the insulation of the bearing. The capacitive discharge current can cause fretting of the bearing and raceways and produces temperatures high enough to melt the bearing steel and cause pitting. If the motor frame is poorly grounded and the motor is connected to a mechanical load that has a proper grounding, low impedance, the common mode current flows through the shaft reaching for the lower impedance. Clean power takes advantage of the latest generation of power transistors, advanced algorithms, and optimized integrated filters to produce the next generation of VFDs without common mode voltage. A clean power VFD is the solution. A three-phase clean power VFD produces three smooth sinusoidal waves, which at any point average a sum of 0. This creates an optimal scenario with zero common mode over voltage. The best solution to mitigate common mode voltage is to not generate it. A clean power VFD produces a clean signal with no need to mitigate common mode voltage.
Just listen to the difference. When a standard PWM inverter drives the motor, you hear the harsh switching noise, audible evidence of compromise. Now switch to the Smart D Pure Wave inverter. The same motor, but the sound is smooth, clean, and nearly silent. That's not just quieter, it's smarter. Superior waveform, superior operation.
Wait.
Yeah, so I'm going to go ahead and let Simon, Simon jump in and give more information on why the technology is different and what its advantages are. So I'll let you go ahead and share there, Simon.
Sounds good. Thanks a lot, Roger. I think everyone can hear me properly, and let me share. You should see my screen now. So yes, as you mentioned, we're here to talk about the Clean Power VFD. And I will aim to present for about 30 minutes, and then we'll have 15 to 20-minute questions. We're a small group, so if someone has a question, feel free to raise your hand in the Zoom. And I'll let you know, either I'll address it right away or we can see it a little bit later. So, of course, everyone who is on the call, I'm sure, knows very well VFD, and I will try to skip parts on VFD theory and keep it to a minimum and really focus on the value add of the Clean Power VFD. But to make sure we all have the same background, let's remind ourselves that VFDs are there because of their tremendous benefit, whether it's a process focus, its reliability for motor, or of course, energy efficiency. But outside of these benefits, they also come with disadvantages that need to be mitigated. And we can put those into two broad categories. Impacts on the grid, mainly harmonics, and impacts on the motor coming from the pulse width modulation, as you've seen in the quick video. And SmartD's mission, really, since our inception in 2018, has been to create a VFD that addresses both the disadvantages on the grid and on the motor. So a truly filterless VFD with low harmonics on the grid and a pure sine wave to the motor. We're going to keep the agenda very straightforward. So we'll talk about the grid side, we'll talk about the motor side, then we'll talk about the technology behind the Clean Power VFD, and we'll conclude by talking about the product and where it can have maximum impact. Throughout the presentation, I'll talk about the VFD reality of today. I'll refer to some lab results. Those were done by third-party lab where they had dedicated motor test bench with long cables, about 500 feet, a dedicated transformer to mimic a very stiff grid, and comparing our clean power VFD, a standard 6-pulse drive from a leading manufacturer, and that same 6-pulse drive with a passive harmonic filter and sine wave filter. And then I'll refer throughout the presentation to different field results and case studies. So let's dive into it right away, focusing on harmonics to start off with. Harmonics, to understand where they come from in a VFD, we just need to remind ourselves of the VFD architecture. 3 parts to the VFD: the diode bridge rectifier, the DC bus, and the inverter. In the case of grid side harmonics, they're mainly caused by the diode bridge, where in this case, it is letting current through only when the voltage is high enough to charge the DC bus. This means that in between these little humps, you have 0 current draw. And so you're having a nonlinear draw on the grid, and that is the core source of your harmonics. And so typically in a 6-pulse drive, you'll have harmonics around 30, 40%, even more if you don't have an integrated DC choke. And the impact for you is you can have interference with sensitive equipment, you can have a poor power factor, but more importantly, the core impact of VFDs, of harmonics, is overheating of equipment. So if you have a transformer, a UPS, all of these need to be oversized because that harmonic content needs to be dissipated as heat. And of course, you also have standard. So in North America, it's IEEE 519 that might mandate you to keep that harmonic content low so that you don't start polluting other equipment on the grid with your own harmonics. Typical mitigation, as you know, line reactor or harmonic filter. Let's look right away how a harmonic filter compares to a SmartD clean power VFD. So here you can see that in the middle, in your middle screen, you have your standard 6-pulse without any filtering. And you can clearly see the current draw that is non-linear, and that's the cause of your harmonics. If you're putting your passive harmonic filter at the bottom, you're back to having sine waves, but you can see at the top with the clean power VFD that you have these sine waves in both voltage and current without any filter integrated. You're also seeing a better power factor, so that's in green at the top. You have almost unity power factor maintained by the clean power VFD without any filter. In terms of harmonics result, you can see your high harmonic content from your standard 6-pulse without filtering. And you can see that both the passive harmonic filter and the clean power VFD reaches to go below 5% harmonic at full load. Now, as I mentioned, this is a test in a lab with a very stiff grid. So in your typical environment, you actually might get below 3% harmonics at full load. You can also see the result in terms of voltage total harmonics distortion. This is the harmonic distortion that the utility is interested in because that's what is polluting beyond your grid. And you can see here that the clean power VFD in green actually outperforms both, of course, the standard drive, but even the standard drive with a passive harmonic filter. Now you could ask me, okay, that's fine for a standard drive with external filters. What about these integrated low harmonics drives? So in this case, you can have a multi-pulse drive. You can also have a active front end drive that integrates an active rectifier instead of the bridge diode bridge. And you also have these matrix architecture, which are AC to AC. Let's first talk about the active front end. Typically, in a active front end drive, they are focusing only on the first 50 order of harmonic. So this is the portion that is on the left of that red line. But everything that is on the right, so beyond the 50th order, is ignored by an active front end, because there's this kind of blind spot between EMI zone and harmonic zone that is not regulated. So that's where you'll typically see manufacturers hide those higher order harmonics, and you can clearly see them in this signature of a leading active front end. And contrary with the clean power VFD, not only can you see even visually that your harmonic content is lower for the first 50 order, but you don't have that blind spot of hidden harmonics. So this already is an advantage of our drive compared to other active front end. Now, if we talk about the matrix architecture does not have a DC bus. So that exposes potential issue. If you have a disturbance on the grid, that will go directly to the motor on one side. And on the other side, because you don't have that DC bus, you don't have that potential boost. So you're limited to an 85% voltage output, which can be problematic in some cases, and certainly in long cable application, which is of interest to us today. But in all of these cases, they are still PWM-based solutions. So on the motor side, you will have pulse width modulation impacting the motor. And just visually, we can see if we take the same signature, not from the grid, but from the motor side, you can see the difference between a PWM type output harmonic content on the motor side and what SmartD delivers. And it's that motor side actually that enabled us to win a low harmonics deployment in data center, where it was mandated to have a choke on the motor side because SmartD did not need that. We could offer both the low harmonic solution and the simplicity of not having any choke on the motor side. So that gave us a smaller panel and a simpler panel, and ultimately won us the job. Now, let's look at this motor side, because I mentioned harmonic, but it's not only harmonics. There are multiple things going on when we have this pulse width modulation. Again, I'm not going to spend too much time because I assume everyone is already quite knowledgeable about this topic, but the pulse width modulation is the way you create this variable frequency signal in current. So you're doing these high-speed pulses, typically between 2 and 8 kilohertz, switching in a IGBT-based drive. So high switching pulses, and with that, depending on the duration of each pulse, you're able to recreate a pseudo signal in current. However, because of these high-speed pulses, you are generating harmonics, and we've seen it in the other graphs. It's a much more messy distribution of harmonics. And just like you have on the grid side, the main impact of harmonics on the motor side is overheating. So your motor is overheating. It needs to dissipate those harmonics in a way or another. So heat, vibration, noise. And you could mitigate that if you really wanted to remove that. You'd have to go to a sine wave filter, as we've seen in the lab results. Well, actually, we haven't seen them. We're going to see them on the next slide. So here you have it. If you really want to go and remove all of that harmonics in the signal, you can see it here. The output of the clean power VFD is pure sine waves, both in terms of voltage and in terms of current. Your typical drive, you can see clearly the PWM in terms of voltage, and you can see how your signal in current is a pseudo sine wave, but you have this choppiness because you can see actually the different pulses there. And to get the same kind of result, you really need to go to a sine wave filter. So short of that, and of course, I don't know of anyone who puts a sine wave filter purely for noise purposes, although actually that's not true. I know one job where that happened. You won't typically do that, but that's the only way to really remove that issue. And if you compare the impact of our clean power VFD with a standard drive, PWM drive, you're going to measure about a 10% difference in temperature. And, we ironically deploy drive to preserve motors so that they don't get the high current peak when you start your motor from a contactor. But in the same time, you're inducing other problems that are actually reducing their lifespan. And temperature is certainly one of the key elements here. By having a higher running temperature, you're actually reducing the lifespan of the motor. And so by going with a clean power VFD, you're going back to the intentional original lifespan for the motor. So we can monitor this in the lab. You saw Roger's video also shows the sound level. We also see that when we go in the field. And so this is a retrofit that we did in a pump station in a municipality about 100 kilometers north of our office. And the interesting thing is not only can you see the different signal quality between our drive, but there's another drive just beside that is a standard drive on the other pump. And so you can see the signal quality, but you can also hear the difference, where in that case, you almost had a 15 dB difference in sound. And this is something that very often people will tell us when they first start up the clean power VFD is, are you sure your drive is working? I can't hear the motor. But really that is the element you are perceiving of the damage that is, the silent damage that's ongoing in your motor. In the meantime, in this case study, let me mention also that this is great. We deliver silence, we deliver clean sine waves, but we also deliver your efficiency you're expecting out of a retrofit. So you really have the opportunity to retrofit more easily and get that full ROI without the complication. Now, that's the first item that comes from the PWM, harmonics. Let's look at the next one, which is voltage spikes. So on each pulses that is coming out of the VFD, you have a spike at the rising edge of the signal. And this problem actually increases as you have longer cable, as I'm sure all of you know. And you have a reflected wave impact where as you have a wave hitting the motor, it gets reflected back and can be combined with an incoming wave. And so you can have your spikes, not only the small spike at every leading edge, but it can get amplified. And the longer the cable, the bigger the problem. And so that not only damages potentially the cable, but also the motor insulation. And so typically, this is why we're going to mandate inverter duty motors. We're going to mandate higher voltage rated cables, and we're going to, depending on the length, require to have a choke, a DVDT filter, or a sine wave filter. And so if we actually go back to the lab, we can clearly see this is with a 480 volt unit, 500 feet of cable, that if you don't do anything with 500 feet of cable, you're going to get near 1800 volt of peaks, of voltage peaks, definitely higher than what your motor and your cable is rated for. On contrary, you can see how you're really delivering a very constant voltage through the clean power VFD, which is essentially equivalent to the sine wave filter. And someone could point out that, well, Simon, the clean power VFD is a little bit higher than your sine wave filter equivalent. And that's true, actually, because your sine wave filter is a big chunk of metal you're putting outside, you're inducing a bigger voltage drop. And certainly in the context of long cables, voltage drop is something you try to fight here. So this is with 500 feet of cable. If we go out in the field, we have this 1,400 feet um, uh, um, use case where you can see how you've got the pumping station on the left. On the right, you have the submersible pump and how the cable is going through the street. And so if you were to retrofit this, you are talking about a huge sum of money to pull out the cable that in this case was actually used cable, non-shielded, even potentially degraded. So you need to pull the pump, you need to pull all the cables, quite complicated. And this is a use case where they actually tried to put a standard VFD first, and it failed. So despite putting a VFD, putting filters, they had to pull it out. It was faulting nonstop. And on the contrary, they put the clean power VFD, no filters needed, directly connected to the drive. You get pure sine waves, go over those 1,400 feet, no problems. And again, you've got a recipe for very quick ROI on a retrofit. You go from a contactor to a VFD, and you don't have to go through the hassle of mitigation and of what could potentially go wrong here. Now, we've talked about harmonics, we've talked about voltage spikes. There is a third killer here, which is common mode voltage. And you've seen it quickly in Roger's video. Common mode voltage is caused when your three phases are not perfectly balanced. If you have three sine waves, the sum of these three sine waves is 0. And so you don't have that common mode voltage. In the case of a PWM, those are square signal. They don't add up properly. And you have a non-zero common mode voltage. This can be actually above 100 volt, and then it hits the motor. The motor wasn't intended for that. You create a voltage potential, which induces a current in the motor, which now needs to get out of the motor, goes through the shaft, through the bearing, and that is what is causing your pitting, frosting, and flooding. Now, that you can put a choke there. You're not going to remove your common mode. The common mode is caused by the core of the PWM. And so all you can do is really try to get that common mode to go elsewhere. This is where the insulated bearing is trying to not impact the bearings. The shaft grounding ring is trying to get the common mode to go through that ring instead of through the bearings. And the common mode choke will do what it can to get some through that choke instead of through the bearings. But you're really not addressing the root cause in all of these cases. And kind of case in point, you can see we go back to the lab, same setup. You can see the level of common mode current with just your drive. And even putting a sine wave filter is not addressing this because your sine wave is just getting some of the common mode current to go through that filter, but it's still reaching your motor. And so with the clean power VFD, you're actually, I can't say you're eliminating everything, but you're taking out 95% of that common mode current so that you don't have that issue. And we also observe that in the field. This is a case where we were approached by a customer that was having recurring bearing failures. And they really tried everything. They had chokes, they had DVDT, they tried replacing the motor, and nonetheless, they kept on having those bearing failures. And they then installed the Smart E Clean Power VFD, and they got a new vibration analysis. So they really had a picture before and after. And that vibration analysis gave a complete new story where nearly 95% of the vibration acceleration was gone. The spike energy, nearly 90% of that was gone. But more importantly, they've stopped having those bearing issues. So we really see how we can go from the lab to the field, and we're seeing in the field the same benefits as what we see in the lab when we compare a clean power VFD, a standard drive, and a drive with filters. Now, what I'd like to address next is exactly how we bring that value to you guys. And this, at the core of our technology, is the silicon carbide Mosfet. And so the last revolution that I'd say powered the VFDs has been the IGBT, insulated gate bipolar transistors in the 1980s. That's really brought more reliability to the drive, scalability also to that architecture. And since then, VFDs have been riding the IGBT wave. Now, in the late 2010, so 2018, 2019, silicon carbide hit mainstream as it was adopted by EVs. And so from that moment on, production went up, and a lot of investment were done into silicon carbide. Okay, great, Simon. Thank you for telling us about silicon carbide, but why is it so interesting? Well, silicon carbide is part of a broader family of semiconductors, which are called wideband gap. They come also with gallium nitride. They both share some core values that make them very interesting. For one, they can switch at much higher frequency without any problems. I mean, IGBTs, you go above 8 kilohertz and you start derating them. Silicon carbide can hit 100 kilohertz, no problem. They have a higher power density. The higher switching frequency means that you have smaller passive components. They have lower losses. They have lower losses both on every switching losses, but also on what we call RDS on, when current flows through them. And so that means you're generating less heat for a same switching frequency. Now, you do need to be careful because the silicon carbide is switching from one state to the other much faster than your IGBT. And that faster switching generates more EMI and also actually causes more DVDT. So if you simply apply, whether it's silicon carbide or gallium nitride, if you apply these new material to your existing architecture, you're going to encounter problems and you won't be able to use it as is. So this is where at SmartD, we kind of had to reinvent the VFD. And so, yes, we wanted to have an active front end to get all those benefits of low harmonic and regen capability. But we use silicon carbide on it. And we use it at a super high switching frequency. So running at 105 kilohertz, using completely new modulation techniques. We integrated to that some self harmonic cluster cancellation. So this purely mathematical, don't ask me a question on that. I don't really understand. Some much smarter guys on my team are doing that. Included that, used a 3-level architecture instead of your 2-level typical architecture. And what you have is a output of 210 kilohertz, but more importantly, we are able to reduce the size of the filter by a factor of 200. So, we say it's filterless for the user, but it's a little bit of a trick there because we actually have very small filters built into the drive. Now, I did mention that you need to be careful about the EMI noise because you're switching at such faster speed. And indeed, if you don't do anything, you're going to have an extra 20 to 30 dB of EMI. So what we did to address that is not only do we have smaller filters for the harmonics, but we combine that with our EMI filter. So it's kind of an all-in-one filter. And the end result is we have 70 dB reduction in differential mode and 80 dB reduction in common mode noise for EMI. What that means for you as you install one of our drive is really you don't need to think about any kind of filtering on the grid. So that is built in. The active front end takes care of that, takes care of that for EMI, and takes care of that for harmonics. Now, if we go on the inverter side, we apply the same recipe. So multi-level architecture reduces the steps and the amplitudes of the PWM built into the drive. We integrate a filter, an output filter, that is also doubles as an EMI filter. And what's really important as we apply this filter is we would need to address the extra DVDT coming out of the silicon carbide. And so if you were not to do anything, and this is where I said you can use it in the existing architecture, an existing VFD architecture, well, what you get is a whole lot of noise. So someone, main manufacturer, takes the silicon carbide, puts it in their existing drive, they would get a bunch of garble to the motor and probably would kill the motor pretty quickly because of that extra DVDT. In our case, because we have these integrated filters, you get a sine wave at the output of the drive, and you get sine wave at the output of 500 feet, 1,400 feet of cables, you name it. We maintain the sine wave throughout that length of cable. So again, we take out the mitigation. So you don't need a sine wave filter. It's built in. Your motor runs cooler and quieter. You don't need to upgrade your motor for an inverter duty motor. You don't need to change your cable. You can use as is. It will work. And you don't need to think about how do I mitigate a common mode that will kill my bearings over time. We're reducing 95% of common mode directly out of the bat. So really, I love this picture. It's a great way to summarize what we do. We're going from mitigation to simplification. Take out these if, these buts, these, hey, my retrofit fails because of harmonics or because of the PWM output or voltage spikes. Just take that out. You don't need those external filters. You don't need those shaft grounding rings. You all have it built in the Smart D Clean Power VFD. And I mentioned it quickly, but our drive is also a fully 4-quadrant drive. So you're able to have full regen capability in the drive. You don't need a braking resistor. This is great on application where you can benefit from this, where you really maximize your energy savings. And you also have that built-in DC bus so that you have that extra voltage boost on the output, and you have that protection from grid disturbance. So last section of the presentation, give you a quick view of what the drive looks like in practice. We have a touchscreen HMI. This enables us to do a quick updates of the drive. So the drive can be fully updated through the USB port. You can kind of see it, it's there. In 5 minutes, you update the drive. If we add new features, new function, HMI gets updated. So you don't need to relearn button. It's very intuitive. You can read if there's an alarm, it's in plain English. Today it's multilingual, English and French, and we plan to support more language in the future, but you really have a ease of understanding with that touchscreen HMI. I/O, nothing much special to mention other than it is a pretty rich I/O drive. So you'll have all of your industrial I/Os there. Should be good for most of your applications. And your analog in can be programmed for either universal input or for a quadrature encoder. We also strongly believe in free or embedded communication protocol. So the drive comes with Modbus TCP and BACnet IP built in. We also have Ethernet IP that will be rolling out very shortly. And all of these are accessible without any additional board. Again, we don't want you to buy external filters. We don't want you to buy external communication boards, we believe everything should be built in. And last but not least, the drive can be fully programmed through a mobile app. The mobile app is available on Google Play and the App Store. If you search for Clean Power VFD, you can download it today and play around with it, because you can do the setup offline. And it's pretty straightforward. Walk through the wizard and you should be good to go. Now, with that, you should be good to open your eyes to what are the opportunities out there. I mean, if I put it in a nutshell, any low harmonic opportunities, definitely good for our drive. Retrofit, probably the best bang for your buck, because you're not adding any external filters, you're not changing the motor, not changing cables. We see great opportunities with a straightforward retrofit, and surprisingly, there are just so many motors still on contactors. So this is a huge opportunity. Anytime where you have lots of filters and is increasing the space, that's a good opportunity. And finally, I did mention also regen. So we do have 4-quadrant capabilities in the drive, so that's an opportunity you should keep your eyes on, open for. With that, I think you got it. Pure sine wave on the input, pure sine wave on the output, no external filters. That's the core of the message, and that's the core of the value prop. With that, I think I am right on schedule, 30 minutes, and I'm open to questions.
Thank you, Simon. I haven't seen any question on the chat. You guys were, I think there was some sort of a problem with the login. So we're a very small group here. If you do have questions, feel free to unmute your microphones and go ahead.
Hey. I wonder about the cost, the added cost of this frequency drive, this good frequency drive, in comparison with the same rating from normal or traditional drives. Is the cost, is this drive competitive from the cost side?
Yeah, so it's a very good question. I'd say, of course, we are more expensive than a standard drive. And we compare it to a system. So if you have filters around it, we're very competitive. If you have only a 6-pulse drive and you're not putting anything against it, we'll be more expensive. So today we are targeting system applications where you benefit from the value add. And every system varies based on what kind of enclosures you need, what are the filtering needs. But I'd say the rule of thumb is, if you have filters before and after, then it's definitely interesting. If you have a sine wave filter, it's interesting. If you have a passive harmonic filter, it's interesting.
So what do you have some figures about the cost of this drive, the increase on cost of this drive in the range of 15 kilowatts to 50 kilowatts power?
Yeah. So we can take contact with you and give you more specifics. But depending on the market and where you are, you're going to look at about 50 to 60% premium on just the plain drive. But again, you need to think about the system. We've seen a lot of installs where you're 40% less expensive, because you need to consider your cabling, your panel, and so on. So as a system, we're less expensive. As a drive, we're more expensive.
Sure. I think without for normal or for traditional 6-pulse drives, we have increasing in cost of in the installation by about 20%. from this without harmonic mitigations techniques. So if you talk about 50% additional cost, I think it is good. If the
Yep.
applications require this
Exactly.
type of drives. Okay. Okay, thank you.
A quick question on the physical dimensions. Are they pretty much same dimensions for standard PWM drive?
Here again, the drive is about 30% more bigger than your standard PWM. I think that is probably something that we're going to be improving.
Okay.
So the one of the interesting thing here is that silicon carbide is evolving, and the way we've developed our architecture, we can benefit from those benefits. So as silicon carbide increases its power density, we should be able to get users to benefit from that too, as well. But of course, today, as I said, we are a little bit bigger than your standard drive.
Okay. How about
So sorry, Simon. The panel is a lot smaller. Sorry to interrupt here. Once you need filters in front or behind, your panel is going to be almost 50% smaller.
Okay.
So the drive itself is 30% bigger, but with everything else, it gets a lot smaller.
I guess my other question too is if you've got a drive that you have to locate rather far from a motor, is this probably your ideal solution? That's the biggest concern I've always had is I don't want to put drives very far from the motors because I know we get the ferro resonance condition and it's a little bit unpredictable because it depends on the wire and the conduit and the exact distances. It sounds like this is totally going to eliminate that 100%. So it may be your only option for a situation like that.
If I'm very honest, the majority of our opportunities are today driven by retrofit and long cables. I mean, we're even seeing people rethink where they put the drive. So they've been paying for panels to put the drive close to the equipment. Suddenly they're like, oh, wait a second. I don't care if I have 500 feet. I'll put it in a mechanical room where it's more accessible and cleaner environment. So there's
right.
Long cable is definitely driving a lot of the discussion, and it's opening the door to kind of new layouts.
And you can use a standard wire from the drive to the motor then.
That's correct. Yeah.
Yeah. Big plus there. Okay.
How long has this product been out on the market?
So we've been around for 8 years. This existing generation has been being deployed for about 3 years now. And so I can't pretend that we have this product for 20 plus years, but it's been designed with a 15 plus a lifetime in mind. We've done accelerated aging testing that shows over 20 years lifespan expectations. We've done MTBF calculations. So it's been designed to be a top tier player, but I won't pretend that it's been around for those 20 years. To bring a new product, we need to start somewhere.
And where are they manufactured?
So we currently work with Celestica. So it's a contract manufacturers that works with us. We have a plant in Malaysia where we do some box build, and we have some also in Montreal, Canada, where we do some box build.
If there is a request for Canadian made only, we can provide that. Some projects require it.
Okay.
Where do you see most of the applications going?
Well, Ram, as I mentioned today, I'd say we have a majority of our projects which are long cables and retrofits opportunities. We do have some harmonic as well, but if I was to give a number and take it for what it's worth, I'd say probably 3/4 of the opportunities are on the motor side and 1/4 on the grid side.
And are there any special requirements for the motors?
No, that's the key is you don't
Okay.
need to have a inverter duty motor here.
Typical long cable applications could be like overhead traveling cranes, where you have bridge drive motors on the end of the bridge, on both ends of the crane. And typically, depending on the span of the crane, it could be 100 feet or more.
That would be a good application, but I won't pretend that we actually have the application layer for cranes today in the drive. So that's on the roadmap, but it is not something we focus on in the short term.
Mhm.
I think one of the biggest places I see and get a lot of interest is in the submersible pump market, deep well. They've got the cables going down. They got a special cable
Yeah.
in the submersible pump motors. Most of those are long distance. Same thing in the ag industry. Center pivots, a lot of long distances, feeds to everything. And so it ends up, creating that opportunity that they didn't even know they were having until they had motor failure. So they ended up, then having to come in when they put a new drive in afterwards. Then, people are pointing fingers, what the cause was. And that's what really started me researching further and further because, as you know, I've been around drives for a long, long time and I've,
Yeah.
installed a lot of them. And there's been a lot of good applications that have never had a problem, but there are applications that did, definitely did show up. So.
Mhm.
And Roger, that's a good thing. I think the ag market has a lot of hidden opportunities because you're also having an impact on your operations through the animals that are impacted by the electrical noise. And we've had a few recent wins there as well. So it's a good one to highlight.
Yeah, you mentioned something about you had up in Maine where a facility had, a lot of problems with their milk cows or something. Or
Exactly. Yeah, absolutely. So stray voltage gives a shock to the animal and they don't want to eat after that. So uh, between not having animals that won't eat and having a contactor, the choice is easy.
Are there built-in diagnostics into the software?
So not we have some lifetime usage of different components of fans and so on. We don't have a layer of analytics on top that so if you want to run it into your SCADA system or whatever, you're free to do that, but we don't offer that layer of diagnostics on top.
Mhm.
Simon, we have a few requests for the presentation slides. So if you're okay with that, I'll send it to people that share their emails here. Mason, Jamie sent you a quick direct message. If you want to share your email there, I'll send it directly to you. Jamie asked the question, what type of control do you have for PMM motor?
Yeah. So we don't currently have permanent magnet motor support in the drive. That too is something we plan on rolling out in over the course of the coming months. Again, same hardware, software update. So
Thank
do you
you.
have the emails you need, Telly?
I do.
Okay,
Just
then
missing Jamie, but I'll find it separately, no problem.
Roger, you want to
okay.
give the
Well, I thank
final
you
words here?
yeah, well, I thank everybody for their time today, and I will create a copy of the there'll be a copy of the video too also that if you want to send me an email, I'll be glad to send them over to you. And thank everyone for the participation today, and look forward to helping you if we can. So.